All right, so last classification algorithm of the mod, support vector machines. And a lot of this material is actually adapted from this textbook. And this is a textbook that I linked at the start of the mod that I think is a really good resource for just getting really into the nitty gritty of any algorithm that you choose. It's also linked at the bottom of this notebook, I believe. Nope, it is not, but I will link it in the Slack channel. But today we're going to talk about really quickly SVMs for classification, which include two main kinds of classifiers, maximal margin classifiers and soft margin classifiers, talking about the kernel trick, and then a quick example. And then as you can see here in the table of contents, after SVM, we'll go into pipelines. And pipelines, if you have seen your Learn Co lessons, pipelines is a very short section. It's really just about how you can make your machine learning workflow a little bit more efficient, so you're not typing up like code over and over again. All right, so for this algorithm, the support vector machine includes support vector classifier. So support vector classifier is a subset of a support vector machine. We'll go through this in detail in a little bit, but basically the support vector classifier is a support vector machine that divides your data set. And we'll talk about what that means in a little bit as well. So all support vector machines, the intuition behind support vector machines, very, very similar across all the different algorithms. The idea is to try and find a plane that will separate your classes in the feature space. So imagine if you have, actually we have an example right here. If we have these, this data, and in just 2 dimensions here, imagine like blue is one class, pink is another class. This plane separates your data. So you can imagine this in higher dimensions. You're just trying to find the line that best separates your data in space. Now, does that concept make sense? All right, so there'll be some details into how that's done. If that cannot be done, if you can't perfectly separate your points into 2 distinct spaces, you can do one of 2 things. So one, you can sort of change the meaning of separation, and basically you're softening your margins, therefore soft margins, which we'll talk about later as well. Or you enlarge the feature space so that separation is possible. Now, this idea of enlarging the feature space we'll talk about later in the kernel trick, but just know that mathematically extremely advanced. I am not even 100% sure exactly how that works, but you can sort of think about it in an abstract way, and I'll explain that for you all later. So right here, support vector machines, or SVMs for short, are used as a general method that incorporates the maximal margin classifier and the support vector classifier. So these are both methods that, again, try to divide your feature space. Support vector classifier, SVC, is a module that you can import in scikit-learn and use straight up. And maximal margin classifier is, I believe, a form of SVC. By definition, a support vector machine is a support vector classifier utilized with a nonlinear kernel. And that will all make sense by the end of this, hopefully. So, all right, the idea is to define some hyperplane, which again was that separator of your data. In p-dimensional space, your hyperplane can be defined like this. And that kind of looks like our linear regression equation, if y'all remember, kind of. It is basically a line in each dimension. So in every dimension, you're coming up with a line that separates your data points to their respective classes. And that's, again, the whole idea of what SVMs are trying to do. So we saw this diagram already. Imagine that this line is going to be the hyperplane that divides our pink points from our blue points. So first, we're going to talk about the maximal margin classifier. So kind of the SVC example, the support vector classifier example, without using any like fancy like kernel things that we'll talk about later. So an SVM, specifically SVC, you're not computing any sort of probabilistic model. You're not saying, right, probability of being in class A, probability of being in class B. That is akin to, for example, if you have logistic regression model, they actually output probabilities of being in each class, and they will classify it as the majority class. Also with models like KNN, if you have like a voting in KNN, maybe like if your K is equal to 10 and like 8 of your points are saying that it's a class A, 2 of your points are saying class B, you can sort of interpret that as a probability of like probability this is class A, probability of class B is like 80-20. And your model will tell you that it is 80. So yeah, instead of doing that, you're literally drawing a line to divide. And so therefore it's not a probabilistic model. So this is just some other diagrams to determine what this is. You can see that with these, in this diagram on the left, any of those hyperplanes will produce your classification model the same way. So again, the problem with this approach is we can come up with an infinite number of such hyperplanes that we can tilt the line back and forth and it'll still serve the same purpose. So
one quick question. So how do we determine which one is the correct line?
Yeah, that's exactly what the next one is saying.
Oh, okay.
So the best hyperplane is the one that is furthest from the training observations on either side. So imagine if you want to properly divide groups of points, the best division line is, for example, let's go with this middle line first, and let me annotate this with some blue. So with this middle line, we want to compute the distance between the points and the line, and you want the smallest total difference, and you're doing this on both sides. So you're computing the distance like this. One thing that is actually part of the math that goes behind this and not as relevant if you're thinking about it conceptually. Now, computing distance, if we're looking at, let's say, this point here and this line here, how do you compute the distance from a point to a line? The distance is always measured by whatever makes a right angle between the point and the line. So, you know, if you're connecting the point and the line, you could say that like maybe this is the distance because it's technically some distance between point and the line. You're always going to use perpendicular lines. So this has to be a right angle. This is only important if you're really going into the math of it, but for now, not so. But just to know, when you're computing distance from a point to a line, it usually refers to the right angle distance, which is the shortest distance from the point to the line.
So this is the rule for any kind of residuals that we are working on, or only for this vector machine?
Yeah, so this is the case for support vector machine, because when we were dealing with residuals in linear regression, we actually wanted the smallest distance, right? But in kind of the same way, you want to, yeah, I guess in the same way we are looking at distance between your point and the line. I will say for residuals, it is not calculated with this right angle. With residuals, you are always calculating it straight down because it's usually on your y-axis. That's diverging. That's gonna get too much of a tangent from what we're talking about now. But basically, the best hyperplane is the one that has the greatest combined distance between the line and points on either side. So you're really just like counting up all of these distances to figure out what line is, you know, you're imagining like, let's say you're a point from the line, you want to be further away from the line to be safely classified, if that makes sense. Cool. All right, so the intuition, and let me clear these. Intuition is that if we've chosen a hyperplane that's far away from the training observations, it should be far away from the testing observations as well, just assuming that training observations and testing observations are similarly distributed. So the distance between training observations and the hyperplane is called the margin. So basically here you can see that if this is our best line, I wish this was a little smaller. All right, if this was our best line, the margin is the closest distance you have between your points. So you can see here that these points here are kind of the closest to the line. And this distance is the margin. if that makes sense. So it's called a maximal margin classifier because you want to increase this distance as much as possible. That makes sense. And that just ties together the fact that we want the best separating line or plane for our data.
Could I interrupt for a second?
Yeah.
So I mean, I guess it wouldn't work for such a, like if there a scatter plot where their points kind of just more distributed than these, where you couldn't draw a straight line, will you just not use this model?
So we will actually talk about that in a little bit. So this, so yeah, you're absolutely right. If you had a data set that looked like this, yes, very easy to fit this classifier, right? Because everything is on either side. Most of our data doesn't look like that. Most of our data is going to have points like purple points crossing to the other side, blue points crossing to this side, and then we'll introduce the role of a soft margin. But also, you can still fit a maximal margin classifier / SVC because it would just compute these to be like negative distances, if that makes sense. Mm-hmm. Yeah. All right. This is some math that I will not get into. I think it goes a lot better with a more mathematical narrative. So if you decide to get into SVMs or SVCs, this will make sense when you read the chapters. All right. So exactly what Henry was alluding to. What if you have situations where you don't have nicely separable data? So quickly, with maximal margin classifiers, it sounds intuitive, but it is not desirable because of two things. One, it becomes sensitive to individual training observations. So let's say, if you have points that are very close to the line, it has a lot to adjust for. And finally, the algorithm won't converge properly if the training observations cannot be linearly separated. So here, in this case, what if you have a scatter plot that looks like this? How will you determine the best line, right? Again, first, if you use scikit-learn's linear SVC, it will, again, still compute the best line possible, but again, you'll have misclassified points. But it brings us to soft margin classifiers. So soft margin classifiers account for that. So rather than seeking the largest possible margin so that every observation is not only on the correct side of the hyperplane, but also on the correct side of the margin, we allow some observations to be on the incorrect side of the margin or on the incorrect side of the hyperplane, which makes sense, right? Like it's very unlikely that in real life data that you'll find perfectly separable data points. So you give it some give. You give it a margin and you also allow points to be on either side, and you actually take into account of that in your cost function when you're computing the distance between your points and the line. So that is taken into account in soft margin classifiers. And again, the math I won't go into right now. Questions so far before I talk about like determining the margin width? All right, so here the value of C, and this might look familiar because we talked about C in logistic regression. C is a regularization parameter. And the way you regularize an SVM or an SVC is by changing this margin. Like how much give do you want to give to your separating line or plane? So here you can imagine that if your C, with different values of C, you have different margin widths. And this is something that you end up tuning with your, you can either do this with grid search or do this just by running it a bunch of times to determine what your best value of C is. You might lead to over or under fitting depending on C, but that is something that you just tune. Questions about that? Just a reminder, C is the inverse of your regularization parameter. So if you want smaller regularization, you have a higher value of C, and the lower value of C is higher regularization parameter. Questions about this? All right, so what if your data looks like this? Right, you can imagine in some cases you might get data that looks like this. The blue on either side are actually of the same class, but then you have like the purple, pink in the middle that are like, blocking something from blocking something from dividing it nicely. So in a situation like this, even with a softened margin, you won't be able to get a good classifier. So what do you do in this situation? You do something called the kernel trick. And the kernel trick is a very advanced mathematical transformation that basically turns your data from, in this case, we have 2D data, and it can transform it into something of a higher dimension to see if it can be separated in any other way. So the intuition is space expansion. So first you're going to enlarge the feature space through the use of kernel, and the kernel trick is basically the thing that expands your dimensions. And then you can fit your support vector classifier in the enlarged space, but in your original space, your decision boundary will be nonlinear, if that makes sense. So imagine you have this data set here, right? This, obviously, you can't draw any line through it that will give it a good classification result, right? And the algorithm sort of does this for you. It thinks about, all right, how can we separate this data if we add more dimensions to it? And so this is actually a very popular example. You can sort of separate it like this. Maybe you add another dimension. You're looking for differences in your data that you can separate it in a different way. And in this case, perhaps you separate it such that your red circle is literally above your blue circle, and then you can just fit your classifier between the two rings, if that makes sense. So the kernel trick is the process of turning something from this to something like this. It's just changing the dimensionality of your data such that it can be separable, linearly separable specifically. And so you can imagine that, all right, this is our data in some abstract space. If we bring it back to here, what will our separator look like? Our separator will end up looking something like, and excuse my bad circle drawing, but it looks something like that. Our separator is going to end up separating our data to things inside this black circle versus outside this black circle, which is what it means by a nonlinear separator. And that's what they mentioned up here. You have a nonlinear decision boundary because of that process of creating more dimensions and then recompressing it back.
So
Questions about
is
that?
this anyway compared with the scaling models when we scale the data and then run? Is there any kind of comparison, or it's like it's altogether a different thing?
I would consider it different. So when you're scaling your data, the thing is you're not adding dimensions. You're not changing the number of columns that you have. When you scale your data, you're just taking one column and just like changing the range of values that it has. Whereas here, you were literally adding more columns, which is pretty cool. Next mod, we'll actually talk about something called PCA, which is a way of reducing the number of columns. But yeah, this is the kernel trick, which is one way of finding other ways to linearly separate your data. Really quickly, I wanted to go over some examples of different kind of kernels that you can do. All right, and just to quickly mention, there is a theorem that covers why enlarging the feature space will help make your data more separable. All right, this is more math, and we're going to skip over the math for now. Oh, let me see if they have any examples of the kernels. I guess not. Basically, in an SVM model, and let me actually do this for you. Scikit-learn SVM. So in SVM, you can see in the documentation here, you can tell it what kernel to try. So here you have a bunch of different kernels that you can use. Linear kernel, polynomial kernel. This is radial kernel, sigmoid kernel, or something that's pre-computed. Typically, especially at this level of data science, you would just try them all, just because it's hard, especially if you have a multi-dimensional space in your data. It's hard to sort of visualize which one would be best. So it's actually quite typical for entry-level data scientists to just try all the different kernels. questions about the documentation. Here you can see we have a regularization. If you have a polynomial kernel, you can tell it how many degrees you want. I think most of these are in relation to the kernel. Yeah, see, this is only significant to the polynomial and sigmoid kernels. And yeah. All right, so I guess some kernels to mention, and I think it is listed here, different types of kernel, the radial kernel, polynomial kernel, and these would just be how you determine how to expand your feature space. All right, we're about halfway through, which is a good place to be for here. Quickly, implementation. So for this same thing that we're importing, something new that I wanted to bring up is time. I don't think I've mentioned this before, but this is actually something that is fairly relevant when you're training models. I'm not sure if any of you have gotten to this stage yet where you have to like wait for your models to train, but that is something to consider. Like, how long does your model take to train? In the future, if you're working for a company that is consistently retraining their models or using their models to test, the amount of time a model takes is relevant. So we'll take a look and see how we can use a time module to see how long our model is taking to train or test. For this, we're going to use our banknote authentication data set, which really just looks at different, different statistical measures to predict banknotes. Looks like that. Do our usual train test split. So how we use the time, and you can call it whatever you want. This is called tick and talk, for tick tock like time. But basically, whenever you call on the time module like this, it literally does a snapshot of what time it is. And then when you take talk minus tick, so you can see here, Python compiles your code line by line. So it's going to take the time before it trains your classifier, take the time after you train your classifier, and look for the differences between those values. So what I'm doing here, you can see I am instantiating my kernel, my SVC model with a radial kernel. I'm going to fit it to my train data and predict on my test data. And you can see that took 0.004 seconds. Of course, this data set is very, very small, which is something that I will talk about in a little bit as well. But bank data, 8. This is only 1,000 data points, which is not enough. So this ran fairly quickly. Really quickly, you see that we actually have a perfectly classified test set, and everything is 1, which is great. Some might say too good, but this is a very small data set, so it makes sense. Questions about the implementation, and especially like with this time object?
Yeah, so I know Edward was saying that he tried to print out a decision tree. It took it forever to run a decision tree. Could you do that to see, oh, is it worth printing something out in advance?
Absolutely, yeah. Let's say, well, this will only give you the timing if you, it'll tell you how long it took to run. So you would have to run it once to just see how long it would take to run. So yeah, not in advance. If you all are interested, there is one library that, not for this purpose, unfortunately, but if you were doing anything in a really long for loop, will give you like a progress bar of how, of like basically how many iterations through the loop it's done. It's called TQDM, and I will link that to you all later, but Python TQDM, oops, what's happening here? With Python TQDM, hopefully they have some GIFs here. Yeah, so if you see, let's see if there are any good examples here. I guess this is just their documentation, but no examples. Basically, oh, this is what it will look like. If you're doing like a for loop here, it'll give you like a little progress bar. This is on their command line, but you can also have it work in your Jupyter notebook. I'll link this to you all. It's pretty easy to follow. And if you search on Medium, there are a bunch of articles that explain how to use it. All right, I'll link that all to you later. But yeah, Any other questions on like SVCs, SVMs in general?
When do you suggest to run SVM? It's like after we run the others or before we run?
That's actually a good question. Like with all the different models that we've talked about, I think we've talked about maybe like 8 or 9. The order in which you run your models doesn't matter. SVM typically is one of the slower models, I will say. So if you have like a really, really large data set, expect SVM to take a while. I remember I was helping to cover for another cohort that was doing this project. Someone's SVM model took close to an hour to run. So if you have a very large data set, especially if you have a lot of dimensions, because you imagine it's trying to compute the best margin, it's really measuring distances between every point in the line. So because of that, I would say like it is a slower model, and therefore I would run all the other models first. But this is just like if I were to decide, okay, if I'm working on this short-term project, what models should I implement? I would probably leave these to one of the last few, especially if you have a big data set, because it will take quite some time to run.
Okay, and one more question. I was looking out a few data, as I told, for health one. There were some data which were talking about reading the X-rays, reading the other CT scan, all the images.
Yeah,
So which model will be the best to test them out?
that's a good question that we will answer in the next mod. But basically, short answer is for image data, because you imagine like every pixel is a value. Usually for image data, we turn to neural networks.
Okay.
Yeah, and we'll actually talk about neural networks next mod. But neural networks, you can sort of think of it as, I like to think of it as like giant logistic regression. Just doing that for every single pixel. But yeah, we'll get to that when we get to that. But yeah, that's a good segue into the next mod.
Okay.
Right. So just to summarize, so SVMs have actually been experimentally very, very successful, just because in the way that it's expanding your feature set and your dimensionality, it just finds new ways to classify your data that aren't necessarily like explicitly have anything to do with your feature set, if that makes sense. Because you're still constrained by, in other models, you're constrained by the dimensionality of your data, like how many columns you have. Whereas in SVM, they're sort of making new dimensions, which is pretty cool. But because of that, it's not interpretable, right? It's harder to say, all right, why was this point classified in this class versus another point? It's less interpretable than that. Things like with, for example, with decision trees or any tree-based model, you can literally say, all right, because it didn't pass this specific threshold, therefore it's in this class instead of the other. Naive Bayes, you have like probabilities for each feature. But for this, it's a lot harder. It's almost impossible to interpret. Optimization is also hard to understand. One thing that it's specifically good for, very high dimensional data sets with low amount of observations. You can sort of imagine why that is. If you have very few data points, but just a lot of different dimensions, it's easier to find a plane to classify and separate your data. And that's why. All right, any final questions on SVMs?
So yeah, will this be also like kind of overfitting model? No.
So not typically. Typically, one, because you can test different margins and also test different kernels. If you are doing enough trials of an SVM model, you shouldn't overfit. And of course, you would do this by comparing your train and test metrics.
Yeah. Okay.
Anything else? All right, so let's go into pipelines. So pipelines is a shorter section, but I think it's a good one to close out the mod, and you'll sort of see why. Here I've linked the pipeline documentation, but what pipelines do is they basically help you put all of the steps of your machine learning modeling process together. So things that we've dealt with in modeling, one, you have a lot of transformations to do. Also, you have your modeling, and then you have to do like your grid search and all of that. Pipelines makes that a little bit easier. So just as an example, let's import all of these things. What we're going to do is we're going to do a couple pipelines, just a standard one to see how it works. We're going to do it with grid search, and then we're going to do a final pipeline. And we'll walk through this together. And what we're going to do is we're going to do it on the same bank data that we were dealing with above. Hopefully in your projects, you'll do a little bit more EDA and actually understand your data set. But how a pipeline works is you can literally give it as many steps as you want, as long as they are defined objects into a pipeline, and then it'll bring your data through the pipeline. Hopefully, as I explained, it'll make sense. So you can see here, I've defined this pipeline, scaled pipeline 1, that will take my data, bring it through the standard scaler, and put it through SVC, this SVC classifier. So the format of this is a list of tuples for two reasons that I'll go into later as well. First, you have the name of what the step is, and you can name it anything you want. It's just so you can identify the different steps, and then also the object for that step. And pipeline is pretty neat because it knows that when you're doing a dot fit, that it will do like the fit transform, and if you're doing a test set thing, it will do just the transform. So here you can see first I'm defining my first pipeline, and you use it in the exact same way you would a model. So here you can see you can do the dot fit, and I'm going to just do the dot score, and that will just print out the accuracy on our test set. So really quickly, we know that from the model above, this was the same model that we had over here. That was a perfect classifier. So therefore, you see that we have a perfect one there. So what we did here was we took our training set and we fit it through the standard scaler. We fit the scaler as well. And then we put it through the classifier. And for our test set, what it does automatically is it will transform it using the scaler that was fit onto your train set. And again, classifies using the classifier that was trained on your train set. Questions about this?
Yeah, the score closer to 1 is the best one, correct?
Yes, the score closer to 1 is best because this, it takes the default score of your classifier to score it. All right, so here, what I'm gonna do now is, because we don't wanna use, I wanna show an example that is not a perfect classifier for grid search. So we talked about grid search on Thursday. Yeah, we talked about grid search on Thursday. What you can do is you can actually feed a pipeline into grid search. So you don't fit a grid search into pipeline. That would be actually really great, but you would fit your pipeline into grid search. So what we're doing here is we're defining a new pipeline, and instead of using SVC, we're going to use random forest just to see. And then I'm going to give it this grid. I'm actually going to make this a little smaller so it runs faster. Let's do maybe this, this, and this for now. And this is defining the grid in grid search. Once that is done, we have our grid search instantiated here, and then we're going to fit our X train, Y train, again, score on our test. This one will take a little bit to run, but we'll take a look and see what the best parameters are. Here we go. So the best score was a 97% accuracy, and these are the best parameters. So based on these best parameters, what I would do is I would feed it into my pipeline, next step 5, leaf 3, mid-sample split 5. Fit my final pipeline on that. You can see all of these hyperparameters. And again, as usual, confusion matrices, just to see how they were classified. And then the reason why you have it set up like this is for certain models or for certain scalars or just anything that you want to put in the pipeline, every object has attributes. Like for example, in your decision tree, you want to see what the feature importances are, and that's something that you can do. From your pipeline, you can extract the feature importances from your random forest. And the way you do that, it actually acts like a dictionary. So because you have the name here and the object here, you can sort of think of these as like key value pairs. You can call on the random forest classifier part of your pipeline by doing this. Let me just do this first. Oops, I wanted to do this. So once you do this, you can see that this extracts specifically your random forest classifier. And then you can do your dot feature importances. And this, unfortunately, I don't have the code putting the features together with their importances, but basically this will map to how important each feature is based on a ratio. It's a ratio, they all add up to 1. And I think, I forget if this is already in order, but there are some, there is some code in your labs that puts this into a graph so you can see what your most important features are. But yeah, that's all I had to share for now. Because we still have time, I can talk about how you could functionalize your code. But yeah, before I move on, any other questions? All right. Before we move on to that, I just wanted to get like a pulse check on how people are doing with that mini project that I sent out. I don't know, has everyone at least tried to implement 1 or 2 models? I don't know, you can like throw it in
2
the
or
chat
3.
or, okay, nice. Yeah, I think it's good to just get practice implementing models, especially before the project. But all right, I'm gonna assume that everyone has run at least a couple models. Let me see, I see something in the chat. Okay, good. Thanks, Steven. Yeah.
I got a question. You said when you're running the other model, the SVM, that sometimes it could be too good. Like, how could a model be too good? Why don't you want to? Why would it, if you got 1s for everything? Why would that be
Oh,
suspicious?
that's only literally because I wanted to show the effect of grid search. If you're with your data and with your model, if you're predicting perfectly, then that's great. I would say I would always be suspicious of perfect models. Maybe because it could be because your train and test set are both, very specific data. And you do have to also think about in context. Like, for example, if I was using this data set and this model to try and predict, I don't know, the authenticity of banknotes, do I also would I consider, I mean, I would have to have some contextual knowledge on banknotes to know like what it is about, like, is this data representative of all the bank notes in the world? I don't know. But if it's not representative, then yeah, like I would be suspicious of a perfect classifier to be able to test on unseen data. That makes sense.
Yeah, that makes sense.
Mm-hmm. All right, so and thanks for putting in the chat, Christina, I see that as well. With the mini project, I would offer this as like an added challenge. If you're comfortable with the implementation of your models, I challenge you to functionalize some of your processes. I think one of the easiest things to functionalize is your evaluation metrics. And I'm actually going to pull up one of my projects to showcase this. Not a perfect project, but I do have functions for it. So this is one of my projects. This is an NLP project, so you can't cheat off this, but it has very similar steps that you would take because it's also a classification project. So one thing I did was I created this model, this function called evaluate that basically will do everything I need. So per model, what this does is, one, it starts time, so you know when. So I can time how long it takes. Start time, end time here to find out how long it takes to train. So here it fits the model. Then it outputs your predictions, and this is where you get your precision, recall, accuracy, and F1 on my train set. And I'll show a summary of this to see what it looks like at the end. And I did the same for my test set. And this time I was just predicting on the test set. And then I output my confusion matrix. So because I wrote this function that, one, trains and tests my model and also gives me all my evaluation metrics that I need, for every single, and you'll sort of see the structure I have here. I basically have a mini section for each model. And I did this as a student. So no, I didn't do this as a student. I reworked this function as a student, but this is not a good notebook because it's not well commented. So don't use this as an example. But what I'm trying to get at is when I wanted to see my modeling process, all I had to do is just write one line of code and I have all my results here. So this line of code does everything for me. Aside from the fact that I have to instantiate my classifier, I do have this one function that does all of that for me and returns my name of the model, my train metrics, my test metrics, also how long it took. And you can see I did this for all of my models. You can see here I just used evaluate. And at the very end, I put it all into a data frame where I had, I think, I'm pretty proud of this myself, but you can sort of see that I have all of my different metrics all in one table with all my different models. And so I have a very direct way to compare and see which model I would choose. And so based on this, I would first maybe I'll look at my test accuracy. So with test accuracy, okay, looks like the highest one is here, naive Bayes, an easy way. I'll just take a look at all the other metrics to make sure that they're fairly high. And in terms of like the time it takes to train and test, fairly low. But yeah, that's like an example of how you could functionalize your process. I will say, when I did this project as a student, I did not have functions in it. This is something that I did after I graduated with a bunch of time. So I think at least trying out functionalizing parts of the process is a good practice. Like for example, you can write a function that will spit out your accuracy, precision, recall, and F1 score, and your confusion matrix all at once. That shouldn't be too hard. But yeah, that's something I really hope to see in this project if you're up for the challenge. Questions about that?
Would you be able to plot this one?
Plot this data?
The summary. So, I mean, with the, graph, like if we are able to write.
Yeah, I mean, I could definitely, like, I imagine probably the best way to visualize this would be like in grouped bar graphs. So for example, if I had a bar graph that looked like this, I would say that, all right, maybe for K and N, these are my metrics, and K and N will be this red bar, and like this will be like maybe test accuracy, test F1, for example, so on and so forth. And then I will look at it for different models just to see how they compare. I don't know if this is a good diagram, if this is a good representation of what I'm trying to explain, but this is how I would visualize this information.
Hey, Ish.
Mm-hmm.
Just curious, the test time, is that in minutes or seconds?
This is in seconds. This is all in seconds.
Okay.
Yeah, so as you can see, support vector machines is typically, support vector machines here took 69 seconds. And this is actually after I reduced the dimensionality of my data. So you can sort of see here, this won't make sense now, but in my data set, I don't know if I have the information here, but I have 4,900 columns, and I actually lowered it to, let's see, where is this? I actually lowered it to 50 columns and then ran SVM just because it takes a long time. So yeah, just some information about that. Other ones that usually take long, boosting models take very long. KNN typically takes long, but I guess not in this case. But yeah. Don't copy my code word for word. I mean, if you find it, and it is typically open source, but I really hope that you do try functionalizing your code on your own. It's a really good practice for just like coding in general. All right, well, that's all I had to share for you all today. Thursday, I'll be introducing the project. I really hope that y'all take this week to decide on your data sets. So yeah, I'll maybe like put a poll on the class Slack channel to see as an easy way for y'all to tell me what data set you're doing. But you do need to have your data set approved by me before you can start working. And hopefully, the sooner you let me know, the sooner you can start. Questions about the project before we get into it on Thursday?
Which one will be a good challenging data set for us?
I will say they're challenging in different ways. So let me actually take a look. I haven't gone very in depth into these data sets, to be honest. So this one, you actually have a little bit of freedom. For the car crash data, you have a little bit of freedom on how you want to group your classes together. So this is trying to see what the main cause of a car accident is, based on like features about the accident scene. So like how many people were injured, did people die, a little bit morbid. But you can decide how you want to bin those categories together. This one is a really interesting one, because this one has actually a bit of sensitive information, in a sense that it is about what's that called, stop and frisk data. So it has some racial connotation, or it has some racial elements in it. And if you do decide to do this, one challenge is to just be very, very aware of your modeling results and whether it's being implicitly biased. So that's also something to think about. Is your model picking up on things that it shouldn't be picking up on? Like, for example, like race. So that's also something to think about. Or yeah, here it says race or gender. So it's very important to be aware of what your model is learning from your data. So that's something about that data set. If you want to be more like socially aware, this is a good one. Customer churn is a good one, because it is it's actually a pretty popular classification problem, just in terms of like customer retention, customer churn. If you want to get into the marketing space, this kind of project is more what's the word? I guess more attractive on a portfolio. And then finally, this water well data, it is an active competition. So because of that, it's more of a challenge, because I believe the classification results that you'll get, it'll kind of like plateau at some point, or you just have to get creative on different ways you can improve your classification results. So yeah, again, you also have the option to choose data outside of this list, but that for those, you definitely have to let me know first.
For the Chicago data, the crash data, it says it's a multi-class classification problem. What does that mean?
Yes. So multi-class classification, meaning it's not predicting between two classes. So usually, and most examples that we've seen throughout this model are like 0 or 1 problems. You're either predicting 0 or 1. For this, you can have multiple classes as your result, basically. But you do have a bit of flexibility. You can actually group things together. So there's actually a lot of different outcomes here. So I think if I see, hopefully it has it in a nice enough format that we can see what the data looks like. So let's see. I'm not sure which one I should be looking for. Here, primary contributory cause. It has many different unique values here, and it's up to you how you want to group them. So you can technically group them to be a binary problem, but I think it would make more sense as a multi-class problem, because you imagine with like car crashes, there are multiple groups of outcomes. But I will say for all of, let me see if that's right. I think almost all of our models, I won't say definitively all because I can't think of all of them right now, but almost all the models work in exactly the same way for multi-class as they would for binary problems. So you shouldn't run into any big issues unless you're doing like ROC curves as a metric. That's something to just like be aware that it's a little bit different for multi-class problems. But I do have the code for that in the logistic regression notebook. Any other questions? Cool. Well, excited to start this project. This is my favorite project out of all the projects, because I think there's just more interesting things to do. Again, try to choose your data set by Thursday. If not, I mean, you will just have less time to work on it. So it's up to you. So yeah, just do that. And also implement more models on that practice data set, because that would be a really good reference point for when you're working on this project. All right, any final questions to close? All right, then, as usual, Slack me if anything. choose your data sets, and have a good rest of your evening, everybody. Bye.